And today we continue our discussion on multivariate probability models. Okay, and this session is going to be a bit more math heavy. All right, so as we continue, what we want to discuss as well ahead is that when we think about multivariate normal distributions or multivariate Gaussians, you know, we should be able to compute the conditionals, the marginals, mainly conditionals. Okay, because when we do Bayesian inference in machine learning, we have some prior distribution, and then we have some likelihood, and then we compute a posterior. Okay, and Gaussians have these special closed form that if the prior is Gaussian and the likelihood is Gaussian, then the posterior is also Gaussian. Okay, so that is why these topics are so important. So let's get started and let's continue. So we have marginals and conditionals of a multivariate normal. Okay, all right. So suppose that we have y as our random variable vector, okay, which has y1 and y2 as my random variables, and this two, they it is jointly Gaussian. Okay, so these two can be modeled by a joint Gaussian distribution. Okay, and of course if it's a joint Gaussian in 2D, we'll have two means, okay, and a 2 by 2 covariance matrix. All right, so say these are the parameters mu1 comma mu2, and capital sigma is denoted by this notation. All right, so if I take the inverse of the covariance, what do I get? The precision matrix. All right, so this is the notation for precision matrix. Okay, all right, so if we had to write the marginal density of y1, what will it be? So I sample y1 from a normal distribution with mean mu1, and what is the variance? Sigma 1 1, because we are if we are talking about marginal, this should be the value, right? And what will be the marginal for this? So mean is mu2 and covariance is sigma 2 2, right? So far so easy, right? But in when we are dealing with Gaussian, so what we have? So we have some prior, and then we have a likelihood, and then we compute posterior. So posterior is basically what? A conditional, right? So we need to have expressions for the conditional, basically the conditional posteriors as well. All right, so we will derive it, but before I derive the expressions, let me write down the expressions because these are very important expressions. All right, so what we have is, so p of y1 given y2. So again, the conditional is also a Gaussian. So this is the beauty of Gaussian, that even if we take the conditional, if the joint density is Gaussian, the marginal is also Gaussian, the conditional is also Gaussian, right? So this is a very beautiful distribution. So y1, all right, and the mean is conditional and covariance is also conditional. Now I'm writing down the expressions which we will derive. Okay, so the expression is, so for posterior mean, that is mu1. If I want to update my mu1, given that I have observed y2, mu12 is basically mu1, the mean for the y1 case, marginal case, plus sigma 1 2. So between 1 and 2, what covariance we have, all right. And then we have to match the units, so dimensionality matching, just a intuitive way of remembering, but we'll derive it, okay, times y2 minus mu2, all right. So is it clear? Good. So that can also be written as mu1 minus lambda 1 1 inverse lambda 1 2. So if you just equate this with its inverse, you get this in place of this, all right. So this equation, if you use, you can get from here to here, all right, y2 minus mu2. And another expression is that in sigma 1 2, okay, lambda 1 1 inverse, all right, or lambda 1 1 mu 1 minus lambda 1 2 y2 minus mu 2. So how did I write it? Because we will also show that sigma 1 2, sigma 1 given 2 is sigma 1 1, okay, minus sigma 1 2 sigma 2 2 inverse times sigma 2 1, all right. So it's just like, sigma 1 1 minus, the product that we do, but this is taken inverse, all right. So we'll derive this part, okay. And basically, so this is posterior covariance, posterior covariance, all right. So these are the expressions, very important expressions, all right. And these are like very widely used in Bayesian machine learning, all right. And this thing, sigma by sigma 2 2, all right, this which we write, which is basically, sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 2 1, this is called as, and of course this was sigma 1 given 2, which is equal to lambda 1 1 inverse, all right. So just don't memorize, just see, all right. And this is called as the Schur's complement. So Schur's complement, okay. So far so good. So what we see that the marginals and the conditionals are also Gaussian, all right. If the joint is Gaussian, marginals and conditionals are also Gaussian, okay. All right. So now let's come to our important derivation. That is, first we understand a bit about how do we take the inverse of block matrices, block partition matrices, and then we use that fact to somehow get to this mean term, okay. So I can just also skip the derivation, but the thing is that if I skip deriving how we get this, then the subject feels more interesting, all right. So first I write the Schur's complement. So first I just give some basic preliminaries before we start doing it. So basic preliminaries, all right. So I hope you all know the inverse of a matrix, right? Very basic, that A inverse A is equal to I is equal to A inverse, all right. And A inverse exists if determinant of A is not equal to 0, all right. And let's say if matrix A is this, then how do we write the inverse? So 1 by determinant of A, which is AD minus BC over here, all right, times you take the transpose of the adjoint. So adjoint is dA minus C minus B, and D minus B minus C minus A, right? So I think this is, you all know. So first is Schur's complement, all right, and here we have the theorem 1. So inverse of a partitioned matrix, all right. Now why are we doing this? It will not seem intuitive now, that why am I doing taking the Schur's complement and all, but you will see the bigger picture by the end of this lecture, okay. So the inverse of a partitioned matrix, let's say M is equal to EFGH. So these are like matrices in itself, EF and GH. And let's say if I want to take the inverse of this, then assuming that E and H are invertible, what we will prove this, that M inverse equal to M by H inverse, all right, minus M by H inverse FH inverse, okay, minus H inverse G M by H inverse, okay, and H inverse plus H inverse G M by H inverse FH inverse. Don't get scared of this. You don't have to memorize it. Don't get scared of this. We will unfold everything, okay? So be with me. And this M by H term, okay, which we will calculate, and we will find it that it comes out as this. So H or E minus FH inverse G, all right? And this is the Schur's complement with respect to H. So of M basically with respect to H. All right. So let's do the working out of the proof. So let me erase this off. All right. So see, we have this thing, all right. What we have is, so we have this matrix M is equal to EFGH, all right. So if I want to, kind of find the I mean, let's say if I do some kind of block diagonalization, then I can always invert it. What I'm trying to say is that, for instance, for example, let's say I want to transform this M into a special structure. Okay, what do I mean by that? So see, I have E, F and G, H, right? And I want to bring in a zero in the non-diagonal place. Okay, I want to bring in zeros in the non-diagonal place. So how can I do that? Let's say if I want to bring in a zero over here, then what can be one approach? So let us say that I have an identity I over here, all right. so I times E minus I times F. So F plus something should give me null, right? So what will that be? So F plus something should give me null. So how can I do that? So if I have, let's say, F H inverse, then I can get a null, right? So did you get my point? What I'm trying to say? We have E F and G H, right? So I want to bring a zero over here in this row. So second row I'm not even caring about. I just keep it 0 I. But here what I should have. So you see, here I have E, all right. And if this has to be 0, the first row second term, then you see F times something should be null, right? So what I'm saying is F, this one and this one, right? So this multiplies with this and this multiplies with this. So F plus some, let's say alpha H should be O. So alpha should be what? It should be minus basically H inverse F, right? Or basically what I can say is, okay, so H is here, so I take inverse the right side. So minus FH inverse, all right? So if I do that, and the reason being, the reason we have it in this way is because you see, if I now make a multiplication, so for this part, you see, what I get is F minus FH inverse H. So H inverse H will be identity. And we assumed what? E and H are invertible in the last slide. That was the assumption. Okay. So this becomes O. All right. Is it clear? I cannot have H inverse F because then if I multiply it, this will not be F, right? So that is why minus FH inverse. Okay. So if I do this, what do I get? See, ultimately I want to find M inverse, right? I want to find M inverse. That is my objective. How can I do that intelligently? Okay. So what I get here, so this is E minus FH inverse G. All right. And what will this be? So this is G and this is H. I hope I am correct in this step. Okay, I am correct. All right. So now I need to break this down further. I want to get rid of this G. So how can I get rid of this G? So see again. I take this matrix and we need zeros over here, right? This time we are not manipulating the first row, but here we have to do a manipulation if I have to make a zero over here, right? So how will I do that? Any ideas? So see, there I did a left multiplication, right? And here I have EFGH and I get this. So I cannot do a left multiplication here because I have to make a zero over here, right? So think this way, that if I can write M in this form, let us say, if I can write say some X times M times Z is some W, let's say, all right, then in that case, if I take the inverse on both sides, what do I get? W inverse, right? So if I do the multiplication, so left multiply with Z and right multiply with X can give me something of this form, all right? So we can get some, well-defined expressions for the inverse, M inverse, right? That is what I'm interested in. So instead of this, what I'll try to do is somewhat like this. So this is like my X, okay, some X, and this is like my M, all right? And this is X times M. So if I write it down, I need to multiply it with something to get 0 over here as well. All right, we need another 0 over here as well because I need non-zero values only along the diagonal, right? So what we can have, so let us say this, I do not play with this part 0I, but here you look that for the first part, okay, for the first part, what we should basically try to give is that, so the first row remains fine because here we did not touch the second row, right? So here we will not touch the first row when we are trying to change. So what you get, so you get some e times something, and of course here also you keep a I mean I basically, okay, because diagonals we are keeping identity. All right, so tell me what should this term be. So it is g, okay, so g times I plus h times something should give me o, right? So from here what will it be? So it should be h inverse g minus h inverse g, right? Because if I have that, then this becomes null. All right, so got the idea? So by doing this, what do I get then? So here I have e minus f h inverse g if I make the multiplication, because 0 times this is 0. All right, and here what will I get? I'll get a simple h, and this is already 0, right? So this is sum of something called as z, that I can call it as z. All right, so now you see the interesting thing, xmz is some w which I have got. All right, so how I can write this down entire thing? So x is this I minus fh inverse 0 I. All right, m is this part e f g h. So this is x, this is m, and I 0 minus h inverse g I. This part is z. Okay, this is equal to w. Okay, e minus fh inverse g 0 0 h. All right, got it? This is w, and I wrote this two steps. So what will be m inverse from here? So this you should keep in mind, like we will use this fact when we break the joint Gaussian into conditionals. Okay, so this you should keep in mind, and I will write it again if I have to, because if I have to explain it in depth. All right, so now coming to the Schur's complement part, what we have is, so basically m inverse equal to z w inverse x. Now see, this is diagonal, so what will be the inverse of this? Just the inverse of individual this block, right? So that is why we were so interested in getting this structure. All right, that is why we were so interested. So what do I get? I can just do a normal multiplication. All right, so let me do it here. M inverse equal to, so z is basically this term I 0 minus h inverse g I. All right, w inverse is going to be, so this is m by h inverse, remember the Schur complement that I was saying, m by h. All right, so we can write it as m by h inverse. So we just write it, because I am writing it because again this is a very big term, and then if I multiply more it will be very complex. So that is why we are keeping a short form for this part, and that is Schur's complement. All right, so 0 0 h inverse. All right, so inverse of w will be just the inverse of the blocks, because we have made it into a diagonal form, right? This is diagonal. So that is why we were so interested in this transformation, because we wanted to bring w into diagonal form. Okay, and then x is basically I minus fh inverse 0 I. All right, so what do we get if I just try to multiply everything? M by h inverse and this is 0 minus h inverse g. Now see, these steps that I am doing is not very relevant right now, because we will just need this fact. Okay, this fact we need. This fact we need. This I am just doing that part for the sake of completeness. Okay, because Shear's complement is a separate topic on its own. So I'm just doing this part for the sake of completeness. Okay, m by h inverse. All right, and this will be h inverse. So this times 0 I. So if I multiply this, what will I get? M by h inverse. All right, and then m by h minus m by h inverse fh inverse. Okay, and then minus h inverse g m by h inverse. All right, and this last term will be a bit bigger, h inverse plus m by h inverse fh inverse. Okay, all right, so we have found m inverse, right? So if m, we take it as this matrix as my covariance, then I can find out the inverse of the covariance. And why are we interested in the inverse of the covariance? Because if you look at the Gaussian expression, it is how, if x you sample from a normal distribution with mean mu and variance sigma, then the equation in the exponential is basically what? Minus half. So x minus mu transpose sigma inverse x minus mu, right? So inverse of covariance. All right, so that is why we have. All right, so now we derive the conditionals of our multivariate normal. The equation that I wrote in the blue box, we will derive that. Okay. Deriving the conditionals of a multivariate normal. So what did we say? That if x1 and x2 are following a joint Gaussian density, then where my mean mu is, let's say, this, and covariance sigma is, let's say, this. Okay, then first of all, how can I write the joint? I can write the joint as p of x2 times p of x1 given x2, chains rule, if you recall. Okay, we can write it. So basically we can say that again it is proportional to this as well, right, or equal to whatever you write, but this is the standard like fact, right, and it's proportional to this times p of x1 given x2. All right, so here we'll do the interesting stuff now. Okay, so if I can write the expression for the the joint Gaussian density, and then if I can factor it into two individual Gaussians, then I can find the resulting mean and the variance for this conditional part. Okay, and that is what I want to do. All right, so that is what we will do. So you see p of x1 comma x2, if I just write the exponential, because I am interested in exponentials only right now, because that is what we will be combining, right? The rest is all normalization constants. So x of minus half. So for the joint, you see we have two means, right? So x1 minus mu1, x2 minus mu2, all right, transpose, okay. And what you had was the covariance, so sigma inverse, and then x2, x1 minus mu1, x2 minus mu2. Now see, here we will use that fact. Okay, so what is the fact that we will use? So you see, try to recall what did we write for, say this was m, say sigma was m, all right? And when I wrote the inverse, how did we write it? So if I just show you, we just proved it, right? That if m is written like this, if m is a block structured matrix, so E, F, G, H are individual matrices, then what did we derive? We derived this. So I minus Fh inverse I, okay, times, or what I should say is this thing, because I have to write for m inverse, right? So basically what we have was m inverse was this. G I, okay, and m by h inverse, and here we have h inverse, all right, and here what do we have? I minus fh inverse 0 I. This we derived in the last slide, right? We derived it. We have derived already. So that is what I'll do. That is why I need this, because this sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2 is like, it's complex, it's a full diagonal, it's a full covariance matrix. I need to break it down into this block form so that I can somehow manipulate this expression, right? So what I can write it out as, so this is proportional to exponential of minus half, okay. Now look very carefully, see the structure, x1 minus mu1, x2 minus mu2, transpose, all right. So you tell me, first is we have I, 0 and I, all right. So what is minus h inverse g? So if you see, this is E, this is F, this is G, this is H, right? So minus H inverse G is what? Minus sigma 2 2 inverse sigma 2 1, correct? Okay, minus sigma 2 2 inverse sigma 2 1. And then what is M by H? Sigma by sigma 2 2 inverse. And this we found the expression for this, right? What term did we got here? The term that we got was E minus F H inverse G, all right? Which was basically what? It was basically E was, so sigma 1 1 minus sigma F is sigma 1 2, sigma 2 2 inverse sigma 2 1, right? Okay. So this 0 0, and what will be H inverse minus, this is sigma 2 2 inverse, all right. So sigma 2 2 inverse, okay. And what is the next part? So I 0 I minus fh inverse. So what is minus fh inverse? So minus f sigma 1 2 sigma 2 2 inverse, all right. So looks big, but we will simplify this part, okay. So what I can write further is somewhat like this. So see, you see, this is some thing, right? So let's say this is some transpose times this, all right. So if I just try to do the whole thing as transpose, I will just take the transpose of this block, okay. I mean, you can expand all the terms if you want to, but that will be like very, I mean, very lengthy to do. So I'm going with some trick. Okay, so exponential of minus half. Try to recall the fact that what was this AB transpose, right? So you know that AB transpose was B transpose A transpose, right? So just that fact that I try to take this thing whole under a transpose. So what we will do is, so x1 minus mu1, x2 minus mu2 will come to the right side, right? Think of this as some A, think of this as some B, okay? So what you get is, you bring this here, and you also take the transpose of this, right? So what you have is, you get something like this. So you have I, and individually also you take transposes. So sigma 2 1 transpose, if you take, you get sigma 1 2, right? So minus sigma 1 2 sigma 2 2 inverse, because transpose of this is because it is symmetric, right? So it will not change. Okay, so you bring this thing here, all right, and then you have x1 minus mu1, x2 minus mu2, okay, and then you take the whole transpose of this part, all right, times this term, sigma by sigma 2 2 inverse 0 sigma 2 2 inverse, all right. And of course, one thing I missed, that I think was this term, right? So x1 minus mu1 into x2 minus mu2, all right. This thing I missed. So this term will again be what? Sigma 2 2 inverse 0 I, all right. So we have something like this. So look at this and this, right? So see, these two blocks are same, just that I have a transpose over here, right? So if I just expand this individual block, then I think we can do something, all right. So if I just expand this block, what will I get? So what I get is, this is exponential of, so we are going a bit down, but okay, just expand this part, okay. So minus half. So what we have, x1 minus mu1, all right, minus sigma 1 2 sigma 2 2 inverse x2 minus mu2, all right, and this will be what, x2 minus mu2, and we have a transpose of this, all right. So it will come out as rho and individual transpose, and this is sigma by sigma 2 2 inverse, all right, and this thing will be x1 minus mu1 x2 minus mu2 x2 minus mu2. Now see, before I do all this multiplication, let me observe something. You see, these two are same, right? And this is diagonal. So just try to look at this thing, this structure that I'm trying to show. What this entire expression looks like, it looks somewhat something like this, right? That, let's say, where you have this, you can think as alpha beta, let's say, all right. So you have something like this. So you have something like this sort, that alpha beta transpose, all right, and this is, let's say, some capital A 0 0 capital B alpha beta, all right. So what is this? If you expand this, what will you get? Very simple. So alpha transpose beta transpose, okay, and then you have A 0 0 B, all right. So if you just multiply this, alpha transpose A alpha, beta transpose B beta, all right. So what does this become then? So this part should become what? What do I get? Tell me, what will I get? So alpha transpose is this, right? So what do we have? So forget about the exp, I'm just concerned with this term, right? I'm just concerned with this bottom term. So what we have is, so x1 minus mu1, okay, minus sigma 1 2 sigma 2 2 inverse x2 minus mu2. All right, this entire thing transpose times a is what, sigma by sigma 2 2 inverse, all right, times this entire thing again, okay, x1 minus mu1 minus sigma 1 2 sigma 2 2 inverse x2 minus mu2, all right, this thing, all right. Now in exponentials, if the powers are getting added up, I can break it into separate exps, all right. So I'll just show that what I'm saying. So one term is this, right? And what is the other term? The one pertaining to x2, right? So look at this, beta transpose b beta, right? So this and this, x2 minus mu2 transpose sigma 2 2 inverse, sigma 2 2 inverse, right? Sigma 2 2 inverse x2 minus mu2. All right. So this thing is clear. So we have exponential of this plus this in the power. So what do we get? So we have exp of, some let's say some k1 plus k2. So what does that become? Exp of k1 into exp of k2. All right. So see, this is very obvious. This form x minus mu transpose sigma inverse x minus mu. This is of course the exponential for p of x2. So what should be this part be? So this entire thing should be the exponential of p of x1 given x2, right? And if I try to look it, then this effective thing becomes my new mean. Interesting, right? So this effective thing becomes my, oops, all right, no problem. So this effective thing becomes my conditional mean, and this part becomes conditional variance. All right. So you got the idea what we are trying to say? Conditional mean and conditional variance. So I'll just erase it and write it properly. Okay. So what I have got is, p of x1 comma x2 is proportional to p of x2 into p of x1 given x2, right? And so this pertains to this. So p of x1 given x2 is proportional to exponential of, so we already broke for this part, right? This part we broke. So we just need to take this part for the conditional. All right. So getting the concept. So you are getting the concept, right? Okay. So this is exp of x1 minus mu1 minus sigma 1 2 sigma 2 2 inverse. Okay. x2 minus mu2. All right. So exp of, actually, so what it is, minus half, right? Minus half this transpose sigma by sigma 2 2 inverse x1 minus mu1 minus sigma 1 2 sigma 2 2 inverse x2 minus mu2. Okay. So mu1 2, the conditional mean is this sigma 1 2. I'm just reading off this term, right? Because we have factored it into that particular form. And sigma 1 given to is sigma by sigma 2 2. And what was that? M by H was E minus FH inverse G, this part. This is M by H, okay? And this thing is inverse, but that is M inverse. So sigma 1 given 2 is this. So that is sigma 1 1, E is sigma 1 1 minus F is sigma 1 2, sigma 2 2 inverse sigma 2 1. Okay, but this part was main, the condition, the posterior mean. And the posterior covariance is there from the Schur's complement, all right? So we have done the derivation, okay? Derived, all right? Okay, so let me get back. All right, so let me write the entire expression once again, all right? And then we move on to conditioning and linear Gaussian systems, okay? All right. Okay, so I'm just writing these expressions down because they are so important and because we will be using them so often that you should not forget. So I'm just writing them in circle. Mu1 given 2 is mu1 plus, you know the notation, right? I have discussed the notation, so you all by now should know the notation, right? I'm just writing it because we will need references to these equations, you know, when we for instance, when we write the posterior precision and all, right? And do shrinkage and all those stuffs, all right? So sigma 2 2 inverse y2 minus mu2, and then mu1. So this is what we derived, and if you equate sigma as lambda inverse, then you will get this expression as well. Inverse lambda 1 2 y2 minus mu2, all right? And that is equal to sigma 1 given 2, okay, lambda 1 1 mu1 minus lambda 1 2 y2 minus mu2. The third equation is writable because sigma 1 2 is equal to lambda 1 1 inverse, all right? If you just do the sigma equal to lambda inverse and what we have done, you will get this result, okay? So this is not, this is trivial. Sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 2 1, all right? So do not memorize these equations, all right? As I'll teach, you know, you will get intuitions for this, that you will see a structure. You don't need to mug this up. You just need to understand how we have derived it, and you just need to see this equation a couple of times, and then it will become like normal. Okay, so I'm just putting a box around it. Okay, so let's discuss about conditioning a 2D Gaussian. All right, so let's take a simple case. Conditioning a 2D Gaussian is just like an example, okay? Conditioning a 2D Gaussian, all right? So what sigma will be? So sigma 1 square, sigma 2 square, right? And what we have, the covariance of x comma y is the correlation coefficient that we studied, rho, times the variance of x1, variance of x2. So rho sigma 1 sigma 2, all right? And by symmetry, same thing, you get, all right? So when you write this p of y1, all right, the marginal, mean mu1 and variance sigma 1 square. So what is the interpretation for a marginal? Let's say I have a 2D Gaussian that is in my joint form, right? This is the joint Gaussian. So when I'm trying to find P of y1, what I'm trying to say is that I take my 2D Gaussian that I have and I project it on the y1 line, and then I get my marginal, right? So this is found by projecting the joint on onto the y1 line, because we have two axes, right? For one for y1, another for y2. So just interpretation, nothing more. And let's say if we observe capital Y2 equals to Y2, then what does this mean? So here this conditional means I slice my joint through the Y2 equal to small y2 line. So here I am doing a slicing. Okay. So this is equivalent to slicing along this line, because I have conditioned on y2. Okay. And so what it should be? So what should be the mean of this? So remember, mu1, that is mu1, okay, plus sigma 1 2 is what? Rho sigma 1 sigma 2. Sigma 1 2, from here I am showing you all sigma 1 2, rho sigma 1 sigma 2. Sigma 2 2 inverse, so here it will be divided, all right, sigma 2 square, or I can say, all right, times y2 minus mu 2. Okay. So you see, so easily we got the, of course, and the variance. We got the mean and the variance for the conditional for a 2D joint after doing all this hard work. Okay. And this will be what? So sigma 1 square, sigma 1 1. So let me write it here, comma sigma 1 square minus sigma 1 2 is what? Rho sigma 1 sigma 2. And you have a sigma 2 1 as well. So whole squared by sigma 2 square. Okay. Now you will see something very interesting implications that I'll cover right now. So what did we get? This thing. Okay. Now think this way. Suppose I give you these terms. For example, say for simplicity, say this is sigma. All right. And so what is this P of y1 given y2 then? So y1 is sampled from a normal distribution with, and let us say that the mean, okay, so we are keeping mu1. So mu1 plus rho y2 minus mu2. Rho is the correlation coefficient, okay? So you know rho, right? Rho is correlation coefficient. So what we get is this, comma sigma square 1 minus rho square. Now see the interesting thing. If I take one case, okay, let us say I take this case that rho is 0.8, all right, and let's say that sigma 1 and sigma 2 is 1 and the means are 0, okay, and let's say y2 is 1. So if y2 is 1, can you tell me what is the expected value for y1 given y2 is equal to 1? That is nothing but the mean, right? The conditional mean. So it's the mean of this, because expectation is the mean. So what is that equal to? So mu1 is 0 plus 0.8 into 1. And this sounds obvious, right? Because if y2, let's say, increases by 1, then because rho is 0.8 correlation, y1 should increase from 0 to 0.8. Okay. So this expected value is 0.8. And another interesting thing, what is the conditional variance? So that is equal to sigma square, that is basically 1 into 1 minus 0.8 square, right? So you see, the variance is not sigma square. The variance is lesser. Why? Because I got some information about y2, that y2 was 1, right? So if I know about y2, and because y1 and y2 are related because of the correlation, then the variance in y1 should be lower than sigma, which is 1, right? But consider the case that if rho was 0, right? In that case, you see, the variance is not changing, right? Because knowing about y2 will not change my beliefs about y1, right? So in that case, this variance does not change, it remains 1. So these equations give a intuition about dependencies. Okay, all right. So you see that as y2 is known, the uncertainty in y1 went down. Okay, so uncertainty in y1 went down. Okay, all right. So the next topic is imputing missing values. And why do we want to impute missing values? So see, if we are given the covariance, we have one benefit, right? Because let's say if we sample, let's say n vectors, each of dimension d, and let us say that in each dimension we did not know, we just know, let's say, about 50% of the data, right, or 50% of the information, then using the covariance matrix or the correlation, we can kind of get an idea of what the hidden uh, values are, right? So there is a process, and we study more about it when we study decision theory, but I'll just give a brief idea about how we do it. Okay, so some parts of my observation or dimension, some parts of dimension y may be missing. So the way to infer is to infer them, we need to exploit correlation. That is, we have to somehow estimate the correlation matrix, right? That is what we have to do. So the matrix is incomplete and we have to estimate it. So we have to exploit correlation amongst the dimensions. So to give you an idea, what I mean by that is, let us say that I am sampling n vectors, okay? So I sample, let's say, n vectors, and each vector, let's say, has dimension d. Each vector has dimension d. All right. So we, let's say, hide about 50% of the data in each row. That is half of the dimensions, we just hide it. Okay. Data in each row. Then what I should do is that, how I should do the computation to infer the missing values is that, so we have n rows, right? So for each row, I can have a joint modeling, right? A joint density, because it's a d-dimensional, let's say Gaussian d-dimensional, right? So for each row, we compute the joint density, which is given by P of, so n comma h means what? For the row n and all the hidden vector and all the hidden elements. So it is basically a vector, right? This is a vector, not a scalar. That's why it is joint. Okay, y of n comma v comma theta. Okay, this is vector. And then what I do is I marginalize this joint for each. So that is, I find the marginal, because this is in a joint form, right? For h can be 50% of the n is like hidden, right? So we marginalize it, that I covered in lecture 1. So we marginalize, and of course theta is basically my mean and sigma parameters. Okay, so for marginals, That is, I take each hidden, for each hidden element that we are considering in that row, I can compute the marginals. So we compute n comma I. Okay, and once we have computed the marginal, we can compute a posterior mean. So posterior mean is the kind of thing that we always compute in statistics, because the it's like the best guess that we can have, and it minimizes the expected squared error. I told about minimizing the squared error. So we minimize the expected squared error. We minimize the expected loss in the population risk concept of generalization. So it's always the expectation that we want to minimize, right? And the posterior mean turns out to give us the best estimate. So we'll study this in statistics part. Okay, so posterior mean, or y bar n comma I, is basically the expected value, and we can approximate the expectations. Okay, comma v given theta. So this is of course a vector, this, but of course this is a scalar, right? Because we marginalized it. So this is a scalar here. Okay, so the posterior mean that we have, it represents the best guess. All right, so it gives me the best guess about the true value of that entry, and in the sense that it is minimizing the expected squared error. So it minimizes the expected squared error. All right, and this is a part of decision theory. So when we study decision theory, we'll cover these ideas, minimizing expected squared error, why posterior mean we get. So you might get posterior mode, you might get posterior mean, and you can get posterior median. Three cases we study when we study the decision theory. Okay, all right. So, and of course another point is that if I want to measure the confidence, because this is my guess value, right? The guess value for my hidden. So to measure confidence, what do we have? Variance, right? So to variance of this part gives me a measure of the confidence in the guess. In the guess value, and posterior mean represents best guess about the value of that entry in the sense that it minimizes the expected squared error. So it minimizes the expected error, you can say, or expected squared error. Okay, so this is the part. Another way is that we can draw multiple samples. Since we have found out the distribution for the marginal, so we can draw multiple samples and we can compute the mean of that. So that is a process that's called as multiple imputation. Okay, so What we talk about now is the linear Gaussian systems, and linear Gaussian systems are, one of the simplest cases of the probabilistic models, that we basically use when we want to analyze the dependencies, correlations between different random variables, right? Because it's a vector. We have a random variable vector, and we want to see the correlations among them. All right. So we want to handle multiple random variables simultaneously, right? And linear Gaussian systems is also an important concept in the sense that, when we study other advanced ML topics or signal processing, these ideas are used widely. Okay, so for instance, it is basically used, in sensor measurements, or aircraft tracking, Kalman filtering that we will study maybe in a future courses also, based on this idea. Okay, and basically, so the idea is that, okay, that if my input is, let's say, in the real world, the way I model is that, I have an input, and my observation is basically a linearized version. So it's a linear model, and on that we superimpose some Gaussian noise. Okay, so let's study it and make it more formal. So linear Gaussian systems. So in the earlier case, like, when we studied the imputation stuff, or imputing missing values, we inferred the missing values based on the visible values, right? But so p of, let's say I wrote y1 given y2, so y2 could be observed, y1 could be hidden, and we wrote the expressions for it. But in real world, what will happen is that the visible part is not like clear, right? There is some noise manifestation as well, right? So a noise is superimposed, and when that is done, we have to infer the hidden part. Let's say z is the latent hidden part that I want to infer, and y is my observation, right? So y is basically a linear combination of the latents plus some noise, plus some Gaussian noise. All right, and so let's see how we write it down and see it more formal. So linear Gaussian systems. And so here we wish to handle noisy observations as well. So earlier case we discussed the ideal like part, but we have to handle noise as well. So to handle the noisy observations, so basically we have some latent that we do not know, and we assume some prior for that latent, let's say Gaussian, and then we have some observation, right? And then we revise our like latents via posterior. And here in this case, we have some noise addition as well, right? So to handle the noisy observations and to infer the posterior, infer my latent. So here latent could be what? Like, let's say there's an aircraft that I want to track, right? And I do not know the location of the aircraft. So I will have some prior assumption that, okay, the aircraft is, let's say, somewhere here. Then I get my noisy observations, right? And on the basis of that, I revise my expected position of the aircraft. So the latents, we are computing a posterior over the latents, right? We're revising the latents. That's what we want to say. So latent, basically the latent posteriors, to infer my latent posteriors. And latent is again, we write it as z, and this is what I'm interested in. Like, for instance, could be location of an aircraft, say, from my radar. Could be location of an aircraft from the radar signal. Okay, so basically, let's formalize it. So let us say that the z be my latent vector. Okay, so this is my unknown vector of values that I'm interested in. Okay, and y be a d-dimensional vector, which is my vector of observed measurements. So let us say I got some blips or the signals from the radar. So those are my measurements, but they are noisy, right? So vector of noisy measurements. All right. So how can we represent it? So you see, I assume some prior over my latent. So I call it as P of Z. So let us say it's sampled from a normal distribution, okay, with let's say some mean mu Z and variance sigma Z. Some like prior we are assuming, okay, and I get some observations based on my latent assumption. So this is again a Gaussian. Okay, so what did I say? The observation is a linear combination of the latents with some Gaussian noise. So let's say sigma y. Okay, so some sigma y variance. All right. So what will be the dimensions of W? So this is L and this is D. So this will be D cross L, right? Okay. Now, how do I write this? The joint is nothing but P of Z into P of Y given Z, right? So what will be the dimensions of this joint? Because we have L and D. So we have one for Z and one for Y, right? So this is a L plus D dimensional Gaussian. Okay. All right. And we will do the derivation for the joint. So what we are doing basically, we will give the expression for the joint, the mean and the variance, and then we will derive it, and then we will use this concept to find the posterior. So it's a bit of work, but if you follow, then I think it will be clear. Okay, so this joint is L plus D dimensional Gaussian. All right, and the parameters of this joint. So why am I interested in this joint? Basically because I want to compute, what I want to compute is this thing, the posterior over my latents. This is what I am interested in, this is what I want to do. But to get to that part, we have to first go to the joint, right? So this that will derive the mu and the sigma for the joint is, so for this it is mu z, and for this it will be what? So mean was wz plus b. So in place of z we put the mean value, right? And the covariance sigma is sigma z. So sigma 1 1, right? Sigma z w transpose, then w sigma z, and this would be sigma y plus w sigma z w transpose. Okay, and this is basically for the joint. Mu and sigma are for the joint density, for the joint Gaussian density. All right. So if somebody asks you what is the normalization constant P of y, how you can compute? So P of y, P of z comma y dy, right? Dz basically, right? And this is what? P of z into P of y given z. So this thing gives me the normalization, right? N of z given mu z comma sigma z into n of y given w z plus b comma sigma y dz. All right. Okay. So if you write it, what you will get is So y is sampled from a normal distribution with mean w mu z plus b, and of course the covariance is this part, right? This sigma yy, because this is for z, so this is for the yy, so z zz zy yz zz, right? So this should be sigma y plus w transpose plus w sigma z w transpose. Okay, w sigma z w transpose. Now we do the derivation for this covariance. How do we get it? So this is what we will try to prove. But if we know this fact, then what we want was this part, right? Posterior for our Gaussians. So I will write that rule as well, and then we derive both of these. Okay. But first I should write the statements. So to compute posterior, that is P of z given y, what we use is the Bayes rule for Gaussians. And how can we compute these Bayes rules for Gaussians? We will use two facts. One is I will use this fact. Okay. So fact 1 from here, and also this fact. And when I use these two facts together, 1 plus 2, when I combine it, which I'll prove after some time, that this posterior, because this is what I am interested in, right? I want to know the revised location of the aircraft given my observation. Okay, as an example. So P of z given y is, so here again z is sampled from some normal distribution, because so the Gaussians are basically closed under Bayesian conditioning, right? So what it means is that if I have a Gaussian prior, we say that it is a conjugate prior for Gaussian likelihood, because the prior is Gaussian, the likelihood is Gaussian. If we combine them, the posterior is also Gaussian. Okay, and we wrote it, right, when we had that P of x1 comma x2 as proportional to P of x1 into P of x1 given x2, right? So when we wrote that expression, when we did the derivation some time back, we saw that P of x2 was coming as an individual Gaussian, and the remaining part was also in a Gaussian form, x transpose sigma inverse x, right? Or x minus mu transpose sigma inverse x minus mu form, right? So this is the beauty of Gaussian. Okay, so first let me write this also down, that because this is an interesting statement, that Gaussians are closed under Bayesian conditioning. Okay, so where should I write it? Gaussians are closed under Bayesian conditioning. Okay, and that means that the Gaussian prior is a conjugate prior for Gaussian likelihood, which means that if the prior is Gaussian, the likelihood is Gaussian, then the posterior is also Gaussian. Okay, so we complete this part, Bayesian conditioning. So mu z given y, sigma of z given y, all right, and so these terms are sigma of z given y inverse is equal to sigma z inverse plus w transpose sigma y inverse w. So try to get some structure. See, for instance, z given y. Okay, just don't mug it up. This posterior conditional variance, okay, or this is the precision, is the prior precision plus some w transpose sigma y inverse w transpose. So if I take some special w's, then I can show that it is prior precision plus n times the measurement precision, which will come to. But try to see the structure, like don't memorize it. Okay, mu of z given y So just from this, so mu1 given 2 is sigma 1 given 2, right? So sigma z given y times, we will derive it, w transpose sigma y inverse y minus b, okay, plus sigma z inverse mu z, okay. All right, now let's come to the derivation part, okay, the interesting part. So first we derive this block. So what you see is we have two blocks, okay. This is one block and this is the second block. All right. So let me erase. All right. So first of all, I write down the joint density, okay. Log p of z given y is basically equal to what? So I can write it as log p of z into p of y given z. Why? Because I have a form for my prior and for my likelihood as well. Both are Gaussian. Okay. So how do I write it? So p of z is basically what? Is proportional to x of minus half z minus mu z transpose sigma z inverse z minus mu z, right? And p of y given z is proportional to x of what? It should be half y minus mu of y, which is what? W mu z plus minus b, okay, and sigma y inverse y minus w, or let's keep it z only because it is conditioned on that. All right. So if I take the log and I combine it, what I will get? I'll get addition of these exponents. And also, since I'm trying to frame it in some, exponential Gaussian form, I only need the quadratic term, okay, and I can ignore the linear and the constant terms because the quadratic term is the main thing in our Gaussian form that we want. All right. So what we have is, let me erase this part then as well. And let me erase this part as well. So this log p of z comma y is equal to minus half z minus mu z transpose sigma z inverse z minus mu z. All right. Okay. Minus half y minus wz minus b and plus some other constant terms that I do not care much about. And look at it. So when I'm trying to frame it as, some kind of basically, some kind of Gaussian, this entire thing, I am only interested in the second degree terms, right, or the quadratic terms, because that is what is creating the influence, right? The linear and the constant terms I can just ignore because I need it in that form, like x minus mu transpose sigma inverse x minus mu. So it has to be in that quadratic form. So the linear and the constant I can ignore. Okay, so quadratic in what? So z and y, right? Either both terms should be z. There are two z's in one term, or there's a z and y, or like you get it, right? So if I expand out the quadratic terms, what do I get? So expanding the quadratic terms, expanding the quadratic terms, okay, in z and y. So let us call it as some q, all right? So this q or the quadratic terms would be, or let's say the quadratic term we take for this log p z comma y. So first is this term, right? Z transpose sigma inverse z from the first expression we get. Okay, then from the second expression, what we'll get? Let's see. So first we have a y with a z, all right? Y with a y, sigma y inverse, y with a y is there, all right? Then what can be next term? Y with wz and wz with y. We have two such terms, right? Y with wz and wz with y. Okay, so for that, what will I get is minus, basically what I get is, so for the first one, like you see, wz transpose sigma y inverse y, and another term is basically minus half y transpose sigma y inverse wz, all right? And what is the last term that we'll get for is the wz with the wz, all right? So that would be basically z. Okay, so we got z, and okay, yeah, so we have a minus half and we get wz transpose sigma y inverse wz, all right? So plus plus minus minus plus, so minus and z transpose, for the first one it's minus, this is again plus, and this is y with wz, so of course here also you get minus with y, so I think that should be a plus sign. This should be a plus sign, right? So overall what will I get? So if you just take the transpose of this, because it's a quadratic form, all right, so we get minus half, we get, okay, minus half, I'm just trying to reorder it. So it is z transpose sigma z inverse z, all right, minus half this term y transpose sigma y inverse y, all right, plus y transpose sigma y inverse wz, all right, and this part is minus half wz transpose sigma y inverse wz. Okay, now the thing is that we need to write it a bit more beautifully, right? Because this is a very long term. So you see, now in the next line you see how I can, write it very beautifully. So this thing can be written like this. So we have a minus half, I take outside, zy transpose, right? So you see, first you have z transpose sigma inverse z. So if here I had some zy, let's say if I had some zy, then to get z transpose and then something here and then z, we should have here sigma z inverse. All right, this is easy. Okay, and what else? So z transpose sigma z inverse z, all right, and basically you have another term that is z transpose, so w transpose sigma y inverse w term comes in, right? But if I just write it down, I'll get it in that form, but that is fine. So basically if I just kind of expand it and let's say write it in this way, let's say alpha beta gamma delta, let's say, so minus half z transpose y transpose, okay, alpha beta gamma delta zy, all right, and so if I just expand it, So Z transpose alpha plus Y transpose gamma, and then we have Z transpose beta plus Y transpose delta. Okay, so this times Z and Y. Okay, and then this expands to what? Z transpose alpha Z. All right, plus Y transpose gamma Z. All right, plus Z transpose beta Y plus Y transpose delta Y. So another point is that, so we have written this so far, and of course since this is symmetric, so beta also has to be equal to gamma transpose, right? So what we get is minus half. All right, so Z transpose alpha Z, right, plus Y transpose beta transpose Z plus Z transpose beta Y plus Y transpose delta Y. So from here, you see that it is obvious that delta should be equal to what? Delta is equal to sigma Y inverse, right? So that we can match. But if you look at other terms, like for instance, this and this part, if you observe, what is this? So this is nothing but C plus Z transpose beta Y. So it is same as, because if you take the transpose of this whole thing, then these two become same. So minus Z transpose beta Y. All right. So minus Z transpose Y matches with which term? So you have here Z transpose, right? But this is Z transpose Z, right? So you have a Z transpose Y. Where do you have a Z transpose Y? So, or basically Y transpose Z. Okay. So Y transpose beta transpose Z. So this is the Y transpose Z term, right? So gamma is equal to beta transpose is equal to sigma Y inverse W. All right. Or you have a minus term because this is plus. Okay. So you equate it, right? This equates with this. So you get minus sigma Y inverse W. All right. And so what is alpha then? So what are the terms we have considered so far? So you see Y transpose Y we have covered here. All right. And for this part, this we have covered here. So we are left with alpha, that is Z transpose Z. So Z transpose Z, and here also we have a Z transpose Z, right? So what is alpha equal to? So this is delta, okay? This is gamma, which is beta transpose, and Z transpose alpha Z is equal to this term and this term, right? So Z transpose sigma inverse plus W transpose sigma Y inverse WZ, right? So I just took it this term and absorbed it here, right? So what is alpha? Sigma Z inverse plus W transpose sigma Y inverse W. All right. So we can write down the final expression. So the final expression is, which is what I was so much concerned about. The final expression will be, so we have written the quadratic form as minus half, okay, zy transpose, all right. Alpha is sigma z inverse w transpose sigma y inverse w, okay, and gamma is beta transpose, that is minus sigma y inverse w, and so beta is just the transpose of it, all right. So for that, what do I get? I basically get a, sorry, minus w transpose sigma y inverse, right, and this is sigma delta is sigma y inverse z y, all right. So this was the quadratic form. So tell me, so look at this expression, and looking at this expression, so log p of z comma y is proportional to this thing, this entire thing, right? Okay. Log p of z given y is proportional to this entire thing. So this is what? X transpose, this is of this form. So some, let's say, um, so X transpose sigma inverse X, right? Minus half X of this. This is what we have in a Gaussian, right? So this we wrote for what? For the joint. That means the covariance of the joint should be this matrix, right? So sigma, or the covariance of my joint, this is sigma inverse actually. Why? Because this is of this form, X transpose sigma inverse X, or the precision, right? So this is equal to what? Sigma z inverse plus, which is what we wrote, right? The base rule for Gaussians. So we have derived it. Minus W transpose sigma y inverse, okay? All right. And then what we have? Minus sigma y inverse W and sigma y inverse. All right. But we are left with one more thing. What is that? So we found out for the joint, but we have to compute for the posterior, right? We have to find P of z given y. And for that, we will take the help of this and the help of this that I was saying earlier. Okay. So let's go further. Let me erase this part. Okay. So this is actually lambda. So lambda zz, lambda zy, lambda yz, lambda zz. Lambda is the precision, right? Because it is inverse of covariance. Okay. So what we have is, from the Gaussian conditioning formula, this is the Gaussian conditioning, okay? So from the Gaussian conditioning rules, what we can say is, firstly, what was mu y, the mean vector that we had? So the mean, if you recall, it was what? So it was mu z and w mu z plus b, right? So mu y will be what? For the yth component is w mu z plus b. All right, this is clear. Now what am I interested in? P of z given y. This is the most interested quantity I want to find out. I want to find out the posterior over the latents, right? So for that, this again, P of z given y that I want to find is sampled from a normal distribution again. So with the posterior mean and the posterior covariance. So how will I find it? I will now take the help of this, because this was also taken from the joint, right? From the joint we came to the posterior mean and the posterior variance, right? So we can use that same fact, right? So what we can write is this thing. So First tell me what is sigma z given y. So sigma z given y, you can think of it as what? Sigma 1 given 2, right? Sigma 1 given 2. Z is 1, y is 2. All right. See the notation. So what is that expression equal to? Sigma z given y. Sigma 1 given 2 is lambda 1 1 inverse. So lambda zz inverse. All right. And what is this? This is lambda zz. So what is the inverse of this? So this entire thing, sigma z inverse plus w transpose sigma y inverse w whole inverse. Clear है? तो ये वाला पार्ट यू अंडरस्टूड, सिंपल है. जस्ट मैंने ये टर्म लिया, आई टेक दिस एंड इट इज इनवर्स ऑफ दैट. ऑल राइट. सो ये वाला क्वांटिटी निकल गया. बेस रूल फॉर गॉसियंस. व्हाट इज द नेक्स्ट पार्ट वी नीड टू टैकल? मीन निकालना है, राइट? सो व्हाट इज म्यू ऑफ z गिवन y? बताओ. सिग्मा 1 गिवन 2, सो सिग्मा ऑफ z गिवन y, दिस टर्म विल बी देयर. एंड देन क्या है? लैम्डा 1 1 लैम्डा zz म्यू z माइनस लैम्डा zy, राइट? zy होना चाहिए. हाँ. y माइनस म्यू 2 is what? Mu y. Okay. This is the thing. All right. So let's expand this out. Sigma of z given y. So what is lambda zz? We computed. This thing is lambda zz, right? Yeah, iska inverse, right? So sigma z inverse w transpose sigma y inverse w times mu z. All right. Minus lambda zy. So what is mu y? Minus w mu z minus b. How did I get this? E expression. Mu y is w mu z plus b. So observe karo, ठीक है? So which term gets cancelled? Acha, what is lambda zy? Lambda zy also, you know, this is lambda zy minus w transpose sigma y. Okay. So plus हो जाएगा w transpose sigma y inverse. अब यहाँ पे यू लुक केयरफुली, W ट्रांसपोज सिग्मा वाई इनवर्स W म्यू जी, W ट्रांसपोज सिग्मा वाई इनवर्स माइनस W म्यू जी. So this and this gets cancelled out, right? So what do you get? Sigma z given y. Okay, so sigma z inverse म्यू जी पहला टर्म, सेकेंड टर्म इसके साथ कैंसिल, प्लस W ट्रांसपोज सिग्मा वाई इनवर्स y minus b. Okay. This is what you get for the mu z given y. ठीक है? So we derived the expressions, right? So finally what did we get? So what I can write? So we can write the final expression sigma of z given y is equal to a वाला term है sigma of z inverse w transpose sigma y inverse w inverse. So the posterior covariance and the posterior mean. Okay. This is equal to sigma of zy sigma z inverse mu z plus w transpose sigma y inverse y minus b. All right. So this is what was the Bayes rule for Gaussians that I was interested in. Bayes rule for Gaussians. Okay. Now using these facts only, we can infer unknown quantities because we want to infer, right? We like, let's say an unknown scalar, okay, or an unknown vector, and while studying this we will explore these ideas of, you know, shrinkage, this prior likelihood posterior, how much does the how close does the posterior deviates, you know, towards the prior, and so on and so forth. Okay, so let's come to that. All right. So let me erase this part and only write down the main equations. So Bayes rule for Gaussians, if I just write down again the formula, all right. Bayes rule for Gaussians, because we will use this formulas further. So I'm just writing it here. Okay. So sigma of z given y is equal to sigma of z inverse plus w transpose sigma y inverse w inverse, all right. And mu of z given y is equal to sigma of z given y sigma of z inverse mu z plus w transpose sigma y inverse y minus b, all right. So we have this, these are the posteriors, all right. Okay, folks. So now we actually discuss about inference, all right. So inferring unknown values, both if we want to infer an unknown scalar or an unknown vector, all right. Inferring an unknown scalar. So suppose that we make n noisy measurements, all right. We are making some noisy measurements, and of course they are y's, right. Y is the observation, noisy observation of some underlying quantity that we are interested in, z, let's say, all right. So let us assume that the observation has some variance, okay. Noise, it has some noise, so it has some variance, right. So the measurement noise has a fixed variance, okay, has fixed variance. So we want to infer the unknown underlying quantity z, all right. But before that, our likelihood of observation, we assume it Gaussian, right. So yi is sampled from a normal distribution, all right, with mean value as the z, which is not known by the way, and variance is lambda y inverse. So lambda y is the precision, all right. And since z is not known, we can assume some form of prior for our z, all right. So it has some mean mu naught and precision lambda. So prior for z, all right, of our underlying quantity z. And what we want to estimate, we want to compute the distribution of the posterior, right, that is p of z, given my observations that I make, right. And of course those observations have some variance, right. So we can take our measurements to be a vector, okay, y1 to, let's say, yn, all right. And see, we want to use this Bayes rule for Gaussians, right. So we want to use w's, we want to place, substitute the value for w intelligently, right, so that we can get some expressions for our posterior mean and posterior variance that we want to compute, right, because we want to estimate the posteriors, all right. That is what we want to estimate, okay. So if I take W to be basically 1 by n column vector, that is, it is just a column vector with n rows, all right, and sigma y inverse that you see over here as, let's say, a diagonal, that is diagonal, so the covariance is, diagonal, and that is a fair assumption, all right. So what is p of z given y? Then we want to estimate this quantity, right, which is sampled from some normal distribution whose mean is, let's say, mu n, and precision is lambda n, and this is the posterior that we want to estimate, all right. So how do we do that? So you see, if I try to write it down, look at this, sigma z given y is should be the posterior, that is lambda n, right. So basically what I am saying, so sigma zy in inverse is this quantity, right, because this is this times inverse. So if I take inverse in both sides, then I get lambda n. So sigma zy inverse is lambda n, right. And what is sigma z? Sigma z is for the prior, right. And what was the prior precision or the prior variance? Lambda naught inverse, right. So sigma z inverse is what? Prior precision, that is lambda naught, plus W transpose. Okay, so what is W? 1n. So W transpose will be 1 occurring n times, right? And what is sigma y inverse? You have diagonals. So you have diagonally, right? So you have lambda y's along the diagonal, all right? And what did we assume? Measurement noise has fixed variance, right? So this is not changing. And then we have W, right? You got this equation. How did we write this? So what did we wrote actually? See, sigma zy is basically what? Sigma z inverse plus W transpose sigma y inverse W inverse, right? So if I take inverse here, so what is this? This is the posterior precision. So this is what? The prior precision, because just the z is for the prior, right? And this is what we substitute for sigma y inverse, right? And this is for the weight W, all right. So going by that basis, what do we get? So lambda n is equal to what? If you just simplify it, lambda naught plus n lambda y, all right. And what else do you have basically? So are we missing anything? No. So lambda naught is equal to lambda n is equal to lambda naught plus n lambda y, okay. So the posterior precision, so you see, as you get more and more measurements, the precision improves, right? So posterior precision, and that should be the case, right? As we get more and more samples, we should actually improve our, I mean, the basically the precision, right? So posterior precision is equal to prior precision plus n times, that is the number of times I make my measurement, times the measurement precision, okay. Because lambda y is associated with observation, so it's the measurement part, right? Got it? Simple. And using this equation, mu of z given y is nothing but mu n, the posterior mean, okay. And so the posterior mean will be equal to what? Look at the equation. So sigma of z given y is lambda n inverse, right? Because sigma z given y, so you can write it as okay, lambda n inverse. And what do you get? So this is for the lambda naught, mu naught, plus again, if you simplify this expression and taking b as 0, what you will get is basically, so you can just actually do the math if you want to. So you have W transpose, right? So what is that? So you have a 1 n times, all right, and then you have lambda y's here along the diagonals and zeros of diagonals, all right, and you have a vector of y. So you have y1, y2, like that till yn. Okay. So if you simplify this expression, what you will get is lambda naught mu naught. Okay. So you have lambda y n times and plus you have all the y's. So basically the summation is n y bar, right? So lambda y can come out. Okay. So if I just show you, I'll just do the steps. Okay. I think it's doable, but I'll just show it for those who actually need it. So lambda y comes outside, y1, y2 up till yn. All right. So it will be sum of yn, which is ny bar. Okay. So 1 by lambda n, lambda naught mu naught plus n lambda y bar. All right. So what we get is, so mu of n is equal to lambda naught mu naught plus n lambda y bar by lambda n. Now we can interpret this posterior mean in many ways. Okay. This is the posterior mean. All right. So how we interpret it is that if you see how I can write it down, so I can just expand the lambda n. So mu of n is basically equal to lambda naught mu naught. Okay. By lambda n is again lambda naught plus n lambda y. All right. Plus n lambda y by lambda naught plus n lambda y into y bar. So you see, this is the prior mean. All right. And this is the maximum likelihood estimate, right? Because what we get, the measurement mean, is what we get as the maximum likelihood estimate, right? So this y bar is the measurement mean or the maximum likelihood estimate. So when we study statistics, we will come to it why it is MLE, why the measurement mean is MLE. And you see that this is what? A convex combination. Why? So this is a convex combination. So this sum is 1, right? Plus n lambda y lambda naught plus n lambda y is equal to 1. So the posterior mean is a compromise or a convex combination between prior mean and the maximum likelihood estimate or the measurement mean. Okay. So how much my posterior, whether it will deviate very far from my likelihood or the measurement precision, or whether it will be closer to the prior, will depend on the strength of the precisions of the prior and the measurement precision, right? Because think this way, if lambda naught is very very large and lambda y or very very small, then of course the shift will be different, right? So we come to that. Okay. So this is a compromise. So posterior mean is a compromise. So posterior mean is a compromise between the prior mean and the maximum likelihood estimate or the measurement mean also, you can say. Okay. All right. And how do we dictate it is basically, if I want to understand the features like things. So see, look at this expression. Okay, look at this expression. Now think this way, that if lambda naught is very very smaller than lambda y, what do we mean by that? That the precision of the prior is very small compared to the measurement precision. or n lambda y, let's say, because that is the measurement precision, then in that case what is happening is that this term will be very small, and because lambda naught is very small, so this fraction will be close to 0, and this term n lambda y by lambda naught plus n lambda y will be very close to 1, right? So mu n, so the mu n will be very close to the measurement mean, all right? On the other hand, so if you consider something like this, let's say if I have a curve, so let us say that we have some density curve, okay? Let us say this is px, okay? And let us say that the mean, so the prior mean is very weak, okay? So let's say this is the prior, it's a weak Gaussian. So let us say it's a Gaussian which has a higher variance, because higher variance means lower precision, right? And let us say that this was my likelihood. So let us say this is likelihood, okay? This is prior. So since the prior is very weak, the posterior will not deviate much, right? So the posterior will somehow look like this only, okay? So this is the posterior. However, if we had some other case, right? So however, if lambda naught was much stronger than n lambda y, or the prior precision was very high, then in that case, of course, mu n will uh, be close to the prior mean. So if it was a very Gaussian with a very low variance, then this posterior would actually shift towards the prior mean, right? So in that case, the posterior shifts towards the prior mean, and this effect we call it as shrinkage, okay? Because of the trade-off between the prior and the likelihood, we are getting the posterior to shift in different places, okay? So this is the shrinkage. This is called as the shrinkage effect. We will write the equations for shrinkage, okay? So let me raise this down. All right, so what we can write is this. We got the equations, all right? So mu of n, which I already wrote and I hope you all have understood, is lambda naught mu naught, all right, by lambda naught plus n lambda y. So it's a convex combination of the prior mean and the maximum likelihood estimate, all right? So lambda naught plus n lambda y, y bar is the measurement mean, or it's also the same as maximum likelihood estimate in this case, okay? All right, so if I have to write down the posterior given my data and the fixed variance sigma square, remember sigma square was the variance of our observation, right? Lambda y, if you remember, was 1 by sigma square, all right? That was what we had, okay? So what is in this case, so z, so we have the, so this is the tau n square is the variance, right? Posterior variance, and mu n is the posterior mean, all right? So tell me, what was lambda n? So lambda n was uh, lambda naught plus n lambda y, all right? So with this, what is lambda n? 1 by tau n square, right? Because precision is opposite of that. And this is what? 1 by tau naught square plus n by sigma square, right? just using this expression and using these facts, right? So tau n square is equal to tau naught square sigma square by sigma square plus n tau naught square. All right, clear? So that's just an expression. And what is mu n? So mu n was basically what? Uh, you wrote it, right? So mu n was lambda n, right? Or it was basically, yeah, 1 by lambda n. So I'm looking at this expression, right? So lambda naught mu naught plus n lambda y bar. All right. So if I put that expression, what do I get? So lambda n is 1 by lambda n is tau n square, right? Tau n square lambda naught mu naught plus n lambda y bar. Now remember, when you actually talk about this precision here, like lambda y and lambda y bar, how do we say it is that? So you basically have, you can think of n lambda y bar, instead of having n measurements, you can think of it as one measurement which has value y bar, but its precision is now n lambda y instead of lambda y. And that is obvious, right? We can always think it that way, that if I'm taking n measurements, then the precision should be high, right? So I took n. So a better statistic of it is the mean. So think of n measurements as taking one measurement whose value is the mean, and of course the precision will be high. So that is n times lambda y. Okay, so what I get here is, so I can just take out the values. Okay, so what we get is sigma square tau naught square by n tau naught square plus sigma square. All right, and what we have, so this is mu naught, 1 by lambda naught is tau naught square, right, plus n by sigma square n y bar. All right, so you can just simplify it. So what do you get? Sigma square by n tau naught square plus sigma square mu naught. All right, plus tau naught square n tau naught square by n tau naught square plus sigma square y bar. So again, here we have a convex combination. All right, so tau naught square is prior variance or 1 by the prior precision, which is lambda naught. All right, and tau n square is my posterior variance. Okay, tau n square is the posterior variance. So I hope these equations now make intuitive sense. All right, now see, when we are doing an update like prior, likelihood and posterior, and see here we are taking n measurements at a time. So you see, if I take n as 1, then I do the update one at a time, right? So let's say prior likelihood, and then I got a posterior, and then again that posterior becomes again a prior for me in the next iteration. All right, so like that we can have sequential updates. Okay, so sequentially we are doing it, that is, we are taking n as 1, so we have some prior, then we see the likelihood, and then we update our posterior and we iterate. All right, so sequential posterior update. The next part is sequential posterior update. Let's erase this part of the board. So in sequential posterior update, what we can write, sequential posterior update. So if capital N is equal to 1, that is the case we take, and the covariance of y is sigma square. So we are taking these values. Let's say this is tau naught square. All right, so these are intuitive, and this sigma 1 equal to tau 1 square is the posterior, right? Posterior variance after my first update, right? So after I make the update, this is the posterior variance. All right. So what do I get? So P of z given y. So the posterior will be I sample z from a normal distribution whose mean is mu1 and the covariance is sigma 1, right? So using these rules, or in fact this equation also, if I use, I can write it, right? So what will be sigma 1? So what is sigma 1? Sigma 1 is basically what? 1 by lambda 1 is equal, so lambda n is equal to lambda naught, all right, plus n is 1, so plus 1 by sigma y, right? So sigma 1 is equal to 1 by sigma naught plus 1 by sigma y inverse. All right. So what can I write it? Sigma naught sigma y by sigma naught plus sigma y. All right. This is correct. And so what is mu1? So that is sigma 1, the posterior times what? So the posterior sigma 1 times, so this is what? This should be 1 by sigma naught, right? So what I can write it as 1 by sigma naught. Why 1 by sigma naught? Because see, sigma z is for the prior, right? Sigma naught is the prior and mu z is mu naught, plus for this is basically what? Or you look at this n times, maybe you look at this part, right? So this part n times lambda y bar, right? So what do you get for that? So n is 1, lambda y is 1 by sigma 1 by sigma y, all right, 1 by sigma y, and okay, and y is 1, so y bar is y, n is 1, so y bar is y. Okay, you got it? I'm just taking from this part. Okay, so see, this is what? Lambda n, which is 1 by sigma n, and here n is 1. Okay, and then what we have is lambda naught mu naught, so mu naught by sigma naught plus y by sigma y. So just look at it a bit carefully, it will be obvious. Okay, you can approach it from any equation, from here or from mu n. Okay, from this part also you can approach, right? So this part also it makes sense, right? So mu1 is 1 by lambda 1, which is sigma 1, lambda naught is 1 by sigma naught, so mu naught by sigma naught, okay, plus y bar is y because n is 1, right? And lambda y is 1 by sigma y, right? So if you look, these two equations are the same, right? These two are the same. Okay, all right. So now we come to this important concept of shrinkage, all right, and so we can write mu1 as equal to, so mu1 is equal to sigma naught sigma y, okay, and this is mu naught by sigma naught plus y by sigma y. Okay, and if I expand it, what do I get? So sigma y sigma naught plus sigma y, okay, mu naught. So you look again, we have a convex combination, all right, plus sigma naught by sigma naught plus sigma y into y. So mu1 is equal to the posterior mean is basically the convex combination of the prior mean and the likelihood. Okay, is it clear? So this is again a convex combination. Okay, so we can just rearrange it because I told about the shrinkage thing, right? So one is you can write it like this, so mu naught you take plus, that means if it is mu naught, so I add sigma naught, so I subtract sigma naught, right? So it is sigma naught by sigma naught plus sigma y minus mu naught. So what I am seeing, how much does the posterior mean is deviating from the prior mean, right? So y minus mu naught is the deviation between the likelihood and the this basically the mean. Or if you look like this way, I can take y outside, okay, from here, and I can write it in this way as well. Sigma naught plus sigma y, okay, mu naught minus y. Now look at the very interesting thing here. This part is the shrinkage, okay. Why? You see, if sigma y is much less than sigma naught, that is, the variance of the likelihood is very small, or precision of likelihood is very strong, right? The variance of likelihood is very weak, or in other words, precision of likelihood is very high, or the prior precision is very poor, right? Is very low. So in that case, you see, since sigma y is very small, this quantity will approach to zero, right? Sigma naught, this thing. So what we get? The posterior is very close to the likelihood. So we see that it will not change. The prior is so weak that the posterior will stay close to my measurement precision only. All right. And in the other case, so in this case, we say that the shrinkage is very small, right? So here we say shrinkage is small. All right. Because shrinkage is small, why? Because mu1 or the posterior mean is very close to the likelihood, right? Because this term is so small. But if this thing happens, right, sigma y much more than sigma naught, then of course this term will be close to 1, so y gets cancelled. So basically mu1 goes closer to the mu naught, right? So in that case the shrinkage is large. Okay, so shrinkage is large in this case. All right. Okay. Another quantity that we often measure is the signal to noise ratio. Okay. SNR, or the signal to noise ratio, which is written as, so what is the expectation or my energy of my underlying latent divided by the expected value of the noise, epsilon square. So remember, what was the formula? Expectation of z square was variance of z plus expectation of z whole square. I wrote this formula in, I think, probability class. All right. So what is the variance? The variance is sigma naught, okay, plus mu naught square is expectation of z expectation of z is whole squared. All right. And epsilon is just a noise, right? So if you see, I sample z from a normal distribution with this parameters, all right, and this is my true signal, okay, and y is equal to z plus epsilon is my observed signal. I said that we add some noise to our latents, right, and that is what we are observing in the real world, right? So observed signal is y, and z is my epsilon is my noise. So if it is noise, it will be from some, so for the noise it is from some normal distribution whose mean we take it as 0 mean noise, and it will have some covariance, right? So what is this sigma y? So this is the signal to noise ratio, or the SNR ratio. So we want SNR ratio to be as high as possible. All right. Okay. All right. Now we move on to inferring an unknown vector. Okay, so we inferred basically a scalar quantity. We computed the posterior. So this is what we're inferring, right? Mu1 and sigma 1 are what we want to are the posteriors. So the posteriors are what I want to infer. All right. So that we did. Okay. Okay, so now we come to inferring an unknown vector. Inferring an unknown vector. All right. So this is not very different from the scalar case, right? Just we have some little bit of concepts, not that complex. So z is my latent that I want to estimate, right? So this is the unknown quantity of interest that I want to estimate, all right? And so we assume a prior for it, z mu z comma sigma z, all right, Gaussian prior. So we assume it to have like infinite variance, that is it's a uniform prior I am talking about. So when the variance is infinite, Gaussian becomes a uniform distribution, right? So, and let's say mu z is 0. So if I have n independent noisy measurements, so I'm taking n independent noisy measurements, okay, of z, that is why we get n yns, all right? So for each measurement, we sample it from a, we sample y from a normal distribution whose mean is z and the noise variance is sigma y, all right? So what will be the likelihood? Since it is independent, the probabilities will be product marginally, marginal product, right? Joint factors into marginal. So z given mu basically sorry yn, because d is the observation, given z comma sigma y, all right? So this is clear. Now we want to show that this is actually the same as, the same as if I am sampling y bar from a distribution whose mean is z and the covariance is sigma y by n, or the precision has come up. Now see, this actually makes intuitive sense, right? That if I am taking multiple samples, if I am drawing multiple samples, then in that case, my precision should improve, right? Or my covariance should come down. So it is saying that the likelihood now, instead of taking n measurements, whose mean is z and covariance is sigma y, we can think of it as if I am drawing just one measurement whose mean value, or that is I am drawing y bar whose mean is z and the covariance is sigma y by n. So the variance has gone down, the precision has gone up, and intuitively it should make sense, right? Because if I am drawing more observations, then the precision should be better, right? So we just give a brief uh, I mean mathematics for it, that how we can write it. So basically, if you look at it, so we have, this is the likelihood, right? So log, and this is the product, right? So p of y1 given z, let's say if n is 2, say capital N is equal to 2, so p of y1 given z into y2 given z. Why? Because they are independent as well, so I could have written this, okay? So what it is, so of course the exponentials are there and the Gaussian has some constant, so let's say some constants gets absorbed here, all right? And what you have is y1 minus z transpose, all right, sigma y1 it should be, or sigma y inverse, okay? So y1 minus z, all right? And for this part as well, you have some, let's say k2 minus half, okay? So you have some y2 minus z transpose sigma y inverse y2 minus z, all right? This is what you have. So just the constants, you can take it out, we do not care about the constants. And what we need is the second degree terms, right? We need the second degree terms, and we need it in terms of zy, right? And the z term has to be there because it is conditioned on z. So what I can write is somewhat like this if I just simplify it down. So it becomes, so we are taking the second degree terms, all right, that you should keep in mind. So some constant is there, I'm not writing the constant, but it is minus half. Okay, so z transpose sigma y inverse z minus 2z transpose sigma y inverse y1, all right, plus z transpose sigma y inverse z again, okay, and minus 2z transpose sigma y inverse y2. Okay, this is what you will get. And if you just kind of write it further, 2 sigma y inverse z, all right, and what you get is minus z transpose. If you take 2 sigma y, you have to so you see sigma y inverse, right, you have y1 plus y2. Now if I want a mean term, I can divide by 2, so I have to multiply by 2 as well, right? So what this is y bar, so what I get is minus half z transpose. So effectively this is the, effectively this 2 times sigma y inverse is the precision, right? So it has become 2 times, right, minus 2z transpose, all right, 2 sigma y inverse y bar. So this effectively we are basically we can say plus some constant, let's say k prime. So this is basically from a Gaussian distribution, all right, which is, whose mean I can say is basically, so I am yeah, basically taking y bar only, so whose mean is z, and covariance is, should be what, it should be sigma y by 2, right? Why sigma y by 2? Because think very carefully, what did I had over here? Some sigma inverse, right, which is the precision, 2 times of the previous precision, that is precision has become twice, that means the covariance should become half, because this is mean and covariance, all right. So precision becomes twice, precision becomes twice. So if n is 2, precision became twice, right? Or if n is 2, what I basically meant was the precision became 2 sigma y inverse, right? So if we take general n, then the precision would be n sigma y inverse, right? N times precision. Okay, so that is why we wrote this proportion. P of d given z, we can think of it as analogous to drawing, as if we are drawing y bar or my sample mean from a Gaussian distribution, but whose precision is significantly much better, n times the precision of the measurement sigma y. Okay, so what we get now is so using this fact, all right, and using these equations, what I can write, so my posterior, if I write, what will it be? So basically we use w as identity, all right, and we take b as 0, and with this we can use this Bayes rule for Gaussians for this vector case, right? So this is what I want to infer. Z given y is the posterior, okay, the latent, the posterior latent is what I want to infer, all right. So y1 to yn, so here mu hat and sigma hat. Okay, so tell me, what is mu hat, what is sigma hat inverse? It's the posterior precision, right, which is sigma z inverse, this estimate sigma z inverse plus n times, so in terms of precision it is addition, right, and you just put an inverse for the variance, right? So this is one thing. And what is mu hat? So it is nothing different, right? I'm just using these equations that I derived, all right, and you just put w as I, so what you get mu hat as, so you have sigma hat, all right, sigma hat into sigma y inverse ny bar we get. Why do we get ny bar? Because w is identity, right? So if you just expand and all, you get ny bar, and b is also 0, plus sigma z inverse is sigma z inverse only, and mu z, right? So these are the posteriors. So we have fulfilled our objective, right, of computing the posterior. So where mu hat and sigma hat are the parameters of the posterior, okay, parameters of the posterior. So basically when you get these temporal sequence of observations like n as 2, so you basically get the generalized version of it. When you generalize it to temporal sequence, you get a Kalman filter. And Kalman filter we will study if we in future cover a advanced topics course. Okay, but I just gave the hint. So when we generalize this to temporal sequence of observations, we have the Kalman filtering algorithm, okay, as a special case. All right. Okay. So just as a very small example, like I was saying about this aircraft thing, right? That let us say that we have a radar, and we make some prior assumption that okay, where my airplane is, which I am tracking, and let's say I get some blips, so I get some observation, and on the basis of that, I sequentially update the location, my possible location of the aircraft, right? So very small example. What we have is basically Bayesian inference for a 2D Gaussian random vector. Gaussian random vector, all right. So 2D why? Because the location can be, let's say, x and y coordinates or 2D coordinates, right? So it's somewhat like this, that let's say that the true location of the airplane is somewhere over here, and let us say that we get a sequence of blips. Because the blips that I am getting from the radar are noisy, so of course they will not be at the correct location but somewhere close. So every time it will deviate, right? So on the basis of these observations, what we do is we think that okay, so the observations are coming from a normal distribution, mean z, and again we have the noise sigma y, because of which it is shifting from the true value, right? So basically the location of the plane is not known, so I'll assume some kind of prior for it, right? So let us say some z sampled from a normal distribution, and we assume some covariance. I2 means second order identity matrix. All right, sigma y is known, the noise covariance is known, but z is unknown, right? That is why I assumed a prior for it. Okay, and yn is this. So if so we assume z with some value, and then we compute p of z, and then we compute posteriors based on what we did in the last slide, and on the basis of that you will see that if initially the prior is somewhere over here, let us say this is the distribution, and let's say the plane was somewhere here, then when you take multiple measurements, let's say n as 10, then you will see that the posteriors will start shifting towards the actual location. So the posteriors shift to the true location as you collect more and more measurements. Okay. And a generalized case of this is the sensor fusion, right? So in sensor fusion, you just have not one sensor but multiple sensors, right? And each sensor is doing the same thing. It's collecting the radar signal. Okay. So in this case, you have also multiple measurements coming from different source sensors, coming from different source sensors, all right? And how can you model it? So the joint, if you want to model the joint, so for you consider all possible sensors, and for each sensor you will have let's say nm observations, right? Okay. And each observation is drawn from a Gaussian distribution, right? Whose mean is z, which is unknown, and the noise covariance sigma m. All right, the sensor covariance noise. So y is basically a n cross m dimensional vector. It's just an example. You don't have to like kind of mug this up. Okay, I'm just giving an example. All right, so this is a k dimensional vector. Okay, and what we want to compute? We want to compute p of z given y, right? So we use the same Bayes rule for Gaussians. All right. So you think this way, that if it's 2D, let's say for 2D or for 2D case, or for the two sensors n equal to 2 case, how do you do? So you get y1 from some Gaussian distribution, right? You sample y2 from some another Gaussian distribution, right? So from the z, you are getting two observations, right? And my likelihood is this. B is 0. So remember wz plus b and sigma y that we studied some time back. B is 0 here. Okay. So w I can take it as identity matrix. Okay. And the covariance sigma y I can take it as this. All right. So using Bayes rule for Gaussians, I can compute the posterior. Okay. Using Bayes rule for Gaussians, the formulas that we wrote for posterior mean and posterior precision, that we can use. Okay. So using Bayes rule for Gaussians, we can compute P of z given y. All right. And another interesting observation that is seen in this case is that if you look, that let's say that you have two sensors. Okay. So let's say this was sensor 1, and let us say this is sensor 2. So if I look along the axis, so let's say this is the x's observed value, and let's say this is the sensor y's observed value, right? So let us say along the axis we are taking two sensors. You see, this is, let's say, sensor 1, and sensor 1 is big. That means it has very high variance, right? And this has lower variance. So when you recall that equation, that posterior is a convex combination, right? The posterior thing settles as a convex combination, right, of the prior and the likelihood. And what we observed there was that there it was prior and the likelihood, right? But if you have two sensors, the idea was same, that whichever's variance is larger, it does not go towards that, right? That means it goes towards that side which has higher precision, right? So see here, S2 has a higher precision, because you see it is not its observed value is confined within a small region, right? So it has lower variance and higher precision. So when you compute P of z given y, the resulting posterior will be closer to S2 than S1, right? So this is the basic funda, because it is the posterior is a convex combination of these stuffs. Okay, so it is, so the posterior is closer to the higher precision side. Okay, it will not be closer to S1. And likewise, if you take a special case, that let's say in one case, let's say sensor 1 has a higher variance along this direction, and sensor 2, let's say, has a higher variance along this direction. Okay, let's say this is sensor 1 and let's say this is sensor 2. So what you will observe is that the resulting the resulting posterior will settle somewhat like this. So it will take the sensor 1's higher precision region, which is along the vertical direction, right? And it will take sensor 2's higher precision direction, which is the horizontal direction, right? So the resulting posterior will be somewhat like this. Resulting posterior distribution will somewhat resemble this. Okay, all right. So this is basically the Bayesian inference for 2D Gaussian random vector, right? So with this we complete this lecture, and in next lecture we'll move on to exponential families. Then we'll discuss about a bit about probabilistic graphical models. Then we'll study mixture models, like they are very powerful models, and then we conclude this chapter. Okay, thank you.